Good afternoon, everyone. My name is Arnold Young, and I welcome you all back to Smart Modium. Now, this is Heat Transfer Lecture Series, and in this lecture, we'll try to derive the general heat conduction equation in Cartesian coordinates. The conduction equation occurs in three types of coordinate system. You have the spherical coordinates, the cylindrical coordinates, and the Cartesian coordinates, and they all have their suitable applications. So in this lecture, we'll try to derive the heat conduction equation in Cartesian coordinates. Now, there's one thing you need to know. Why are we deriving this equation? So our aim for, but first, let me write down the heading. General heat conduction equation in Cartesian coordinates. Now, what is our aim? So our main aim for the derivation of this particular equation or system of equation is to one, find the temperature distribution. That is, get an idea of how temperature is distributed over some area during the heat flux flow. So temperature distribution, let me spell distribution, was a distribution through, or let me say within a medium, through or within a medium. Now the next reason is to find the heat flow rate. So in this case, in terms of conduction, that is how heat is conducted through a material or through a medium, right? Yes, that's the main, these are the two main reasons why we need to develop or derive the general heat conduction equation in the Cartesian coordinate. Now, for this particular derivations, we have to make some assumptions. These are general assumptions, they are not specific. They are general and they are practically applicable. So these assumptions are, that is zero macroscopic bulk motion. I explained macroscopic bulk motion to you the last time. I said macroscopic bulk motion is the same as advection, right? That is when you have several fluid molecules or fluid particles moving in a specific direction. That's basically macroscopic bulk motion. Now, I said that convective heat transfer is conductive heat transfer plus advective heat transfer. Now, what is conductive heat transfer? You have a material, you subject one part of the material to heat. Now, what happened? The atoms over there are actually locked in their lattice. They actually don't have any net motion from their initial position. That is after they've gained the energy, the kinetic energy by, absorbing the heat energy from the heat source, right? That is basically conductive. So if I'm an atom within a conductive material, when I gain energy, that is I start vibrating, colliding with the adjacent atoms to me. They also gain energy, and the collision and transfer of kinetic energy traverses throughout the entire solid material, if I should say, or the material subjected to the conductive heat transfer. Now, that's basically a typical example of zero macroscopic bulk motion. Now, if you have a bulk motion, a typical example of bulk motion is when you have water on fire. When you are heating water, you subject the bottom, that's water layer containing the several water molecules, to heat. Now what happens? They gain energy, collide with the adjacent layer of water molecules. But then as they are colliding with the adjacent layer of water molecules, some of the water molecules are also moving, also undergoing what we call macroscopic bulk motion, and that's basically what we call advection. So for this particular scenario, that's for the derivation of the general heat conduction equation, we assume that there is no macroscopic bulk motion, so the macroscopic bulk motion is zero. Now the medium is of constant density, so we have a constant density medium. Now the specific heat, So the specific heat capacity at both constant pressure and constant volume are all constant. So Cp and Cv are all constant. Hope we know what these are from thermodynamics. These are the specific heats at constant pressure for Cp, at constant pressure for Cp, and constant volume for Cv. But then for solid materials, these are almost the same. For solid materials, or if I should say for incompressible materials. So for solids plus liquids, because liquids are generally incompressible. So for incompressible material, that is incompressible. For incompressible material, the Cp is the same as the Cv and it is constant. Now, these are the assumptions for the derivation of the general heat conduction equation in the Cartesian coordinate. First, for us to derive the equation, what do we then have to do? Now, we have to get our coordinate system. So our coordinates, we know the normal coordinate system. That is, so this side is denoted the y-axis, this side is the x-axis. I'm assuming this side is the z-axis, right? This side is the z-axis. Now, this is what you need to know. This is basically your coordinate system. So what do I do? Now, for me to derive the equation generally, then I will select, let's say I have a large solid material subjected to heat, or a large solid material subjected to heat. So let's just say I've subjected one phase of this particular material to heat. The heat will transfer right throughout the entire material. What then do I do? I'm selecting small infinitesimal control volume, or if I should say small change in volume within this large volume to do my analysis. Then I can derive the conductive heat transfer equation, the general conductive heat transfer equation for my analysis. So that is what we'll be doing. So I'm considering a small control volume within a large material. That is what I'm doing. I'm considering a small control volume within a large material. Now this is my control volume, and since this is a system, it needs to have a boundary. So this is the boundary of our selected system. This is the boundary of our selected system. This is the boundary of our selected system. Now this particular axis is, as we assumed, our z-axis. This particular axis, as we assume, is our x-axis. This axis as well is our y-axis. Now, beautiful. Now, there's one thing you need to know. Since this is an infinitesimal small volumetric element, now let's say heat, when the whole material, when the large material is subjected to heat, what happens? The heat is transferred. So for this infinitesimal small volumetric element, I'm also going to say the same thing. For this particular phase, say heat is moving along this axis, and along x-axis we mean heat is moving along the x-axis. Then I said the heat flow rate along the x-axis will be Q subscript x dot. This is quite understandable. The heat flow rate along the x-axis will be Q subscript x dot. Now, the heat flow cuts this particular surface and shows up at this particular surface. Now, when it shows up at this particular surface, what will be the heat moving out of our control volume along the x-axis? It will be, we know this from calculus, it will be Q dot subscript x plus dx, because during the transfer of heat through the what do you call elemental volume, what happens? The change in, that is the change along the axis, was dx. And then the heat, the quantity of heat at the other side, that is after I've crossed, that is after I've left the boundary of the dx, what will be the quantity of heat? It will be Q dot subscript x plus dx. Then that is this particular heat quantity. Now the same thing applies to the heat flow along the other axis. So along the y-axis, it will also be the same thing. So let's just say along the y-axis, this is my heat. Now it is Q y dot, that's the heat flow rate along the y-axis. Now when it leaves the control volume, the quantity will be, because the heat could have changed, right? The quantity of heat would have changed after the flow had left the volumetric element. So Q dot plus that infinitesimal change, supposed to be Q subscript y plus my infinitesimal change in y. Now the same thing applies to the z-axis. Let's just say my heat flow is along here, so it is entering into my infinitesimal, that is volumetric element, has Q z dot. Now when it leaves the volumetric element, it leaves as Q dot z plus dz. Yes, and mind you, since this is an infinitesimal volumetric element, then I can say that the dimension along the z-axis is also dz. Similarly, the dimension along the y-axis is also dy. Then I can say the volume for this particular infinitesimal element, or my control volume, would be dv is equal to dx times dy times dz. Now, I'm assuming a general scenario. So it could be that during the flow of heat through my infinitesimal volume, there was one time rate of change of energy, in this case thermal energy, within my infinitesimal control volume. So the time rate of change of the thermal energy, I'm representing it as change in E dot. Now, similarly, as the heat was moving through my control volume, there was also heat generation within the control volume, because we are not assuming that the heat flow is actually steady. No, we are not assuming that. It could be that within the infinitesimal control volume, there was heat generated. And that heat generated, I'm representing it with J dot. That's the heat generation within the control volume. Now, you may probably see in other books, don't get confused. Wherever you see that is ES in other books, it means here my change in, that is the thermal energy. The time rate of change in ES will be the time rate of change in my thermal energy. That is all what I mean here. Now, in other books also, when you see QJ dot, that's the time rate of heat generation within the infinitesimal volumetric element. It is the same as my J dot here. So when you see this, shouldn't get confused. Now, the rate of heat generation per unit volume, in other books you see Q double dot. It is the same as J dot. So just in case I use J dot throughout, don't get confused. So this is the time rate of change of, that is heat generation. Not time rate of change, the time rate of heat generation instead. The time rate, there's no change here. So the time rate of heat generation within the control volume. The time rate of change of heat generation within the control volume per unit volume, So wherever you see J dot, small j dot, I mean Q double dot. So please don't get confused. Now, there's one thing you need to know. After defining all these terms, what do we do? Now, from conservation of thermal energy, what does conservation of thermal energy say? From thermodynamics, conservation of thermal energy. What does it say? Now, whenever you have a control volume, it says that is the heat entering into the control volume. That's the heat influx. So the heat influx plus the heat generation. I believe you remember this from thermodynamics, is equal to, that is the heat efflux, that is a heat leaving out of our infinitesimal volume, in this case, which is our control volume, plus the heat generated within the control volume. So the heat generated within our control volume, within the control volume, CV. Wherever you see CV here, I mean control volume. Wherever you see CV here, I mean control volume. Then mathematically, representing this particular statement with symbols, it is so simple. Now, how do I write this? Now, when you check from my infinitesimal control volume, now you realize that Q subscript X dot is entering into the control volume. Q subscript Y dot is also entering into the control volume. And Q subscript Z dot is also entering into the control volume. So the heat influx will be, that is Qx dot plus Qy dot plus Qz dot plus the heat generation, as I said, is J dot is equal to, now what is my heat efflux? That is the heat quantities or the heat flow rate out of the control volume. They are Q dot subscript X plus dx, Q dot subscript Y plus dy, Q dot subscript Z plus dz. So those are the heat quantities leaving my control volume. Then I end up with, that is Q x plus dx dot plus Qy plus dy dot plus Qz plus dz dot, that's my heat efflux, plus heat, oh sorry, this is not supposed to be heat generated within the CV. It is the time rate of heat change, the time rate of change of thermal energy, if I should say. That's what I represented with change in E dot, the time rate of change in thermal energy. So note the time rate of change in thermal energy. Time rate of change in thermal energy. Time rate of change in thermal energy. Now that is it. So I can write here change in E dot. So this is basically your conservation of thermal energy. This is the conservation of thermal energy. Now we know, let us define certain terms over here. Now my J can be written as I said, this is my heat generation, and the heat generation formula is equal to, that is the volumetric, or the heat generation, the time rate of heat generation per unit volume multiplied by the volume. In this case, the volume is dV. That is one thing you should know. So the G, which is the heat generation within the control volume, is that is the heat generation per unit volume times the volume of the infinitesimal control volume I've selected. That is it. Now, before I proceed, I want you to remember this from partial differentiation, from differential equations. Now, you remember from Taylor series, when you have Q subscript n plus, say, the n, the differential of some particular axis or some particular independent variable, it can be written as that is Q subscript N plus del Q N divided by del N multiplied by the N plus some higher order terms. Now those terms can be taken as 0 because that is we are going to get terms containing that is my dn all squared, my dn all cubed, and it goes on. And since we selected an infinitesimal control volume, then we can assume that the change in those parameters are all approaching 0. So the change in, let's say, the square of the change in x is approaching 0. The cube of the change in y is approaching 0. The cube of the change in z is approaching 0. So the higher order terms will all approach 0. So I can say this goes to 0. Then I can say that from Taylor series, that is for infinitesimal, for my infinitesimal control volume I've selected, my Taylor series is basically this. My Taylor series is basically this. Then if my Taylor series is basically this, then I can say that my Qx plus, that is dx, the rate of, Q subscript x plus dx can be written as, that is Qx plus del Q subscript x divided by del x dx. Similarly, Q dot y plus dy is equal to Q. These are all rate quantities. Y plus del Qy divided by del y dy. Similarly also, my Q subscript z plus dz is equal to Qz plus del Qz dot divided by del z, not y, del z dz. So we are going to substitute this into the conservation of thermal energy equation. Let me move to a fresh page. Let me state this here again. We said that is my Q subscript x plus dx is equal to, that is Qx plus del Qx. These are our rate quantities divided by del x plus dx. Q subscript, that is y plus del y is equal to my Q subscript y plus del Q y divided by del y times dy. Similarly, Q subscript z plus dz is equal to Q, these are rate quantities, Q subscript z plus del Qz divided by del z times dz. These are quite, then our conservation of thermal energy equation was what? Conservation of thermal energy equation was, that is Q, that's the energy moving in, Qx dot plus Qy dot plus Qz dot plus, that is the energy generated within the control volume, which was G dot, is equal to, that is the energy leaving out of the control volume, which was Qx plus dx, that is plus Qy dy plus Qz dz plus the time rate of change of thermal energy within the control volume, which is change in E dot. This is quite understandable. Then I also said that is the heat generation within the control volume can be written as, that is the heat generation rate per unit volume times, that is the infinitesimal volume, or the volume of our control volume we've selected. That is it. Now let us do the substitution. Now substituting it into the equation, we can say that Q subscript x plus Q subscript y plus Q subscript z, right? Minus, okay, you let me take my time for everybody to understand. Plus, that is G dot is equal to, this becomes Qx plus, that is del Q, these are it, del Q del x dx plus Qy del Q del y dy plus Qz del Q del z dz. Yes, so this is the equation. Now I can do certain things to the equation. Now I realize that these equations, as I said, right, are all rate equations. Bear in mind, all these quantities, the Q dot, all the dot quantities are are rate quantities. Bear in mind, yes, they are all rate quantities. Now we can cancel out some of the terms here. If you can see, I'm supposed to bring, that's the time rate of change in thermal energy within the control volume. I forgot to bring it. This is it. Now, canceling out some of the terms, you realize Q raised to the power dot x cancels out this particular term. It is obvious. It cancels out this particular term. Now, you realize this term also cancels out this particular term. This term also cancels out this particular term. Then what do we end up with? We end up with, that is J dot is equal to del Q del x dx plus del Q del y dy plus del Q, all subscript, this subscript x, this subscript x, this subscript x, this subscript y, this subscript y. Now I'm bringing subscript y there because now from the Taylor series, if Q dot subscript x, I mean y plus dy is equal to Q dot y plus, then the derivative of this has to be the derivative of the heat flow rate along the y-axis with respect to the y-axis. That's the reason why I'm bringing the subscript here. So this is supposed to be y x, this will be z dz del z dz, then what else, plus the rate of change in the thermal energy within our control volume, Now I know I don't know if you remember this from the first lecture. I said something, I gave you some particular formulas. Now I said that if Q dot subscript n is equal to negative Kn, now not if, I said according to Fourier's law, not even if. According to Fourier's law, that's the heat flow, the conductive heat flow along some particular axis can be written as a negative as K along that same axis multiplied by, that is the cross-sectional area perpendicular to the heat flow along the n-axis, right? Multiplied by, that is the partial derivative of the temperature field with respect to the axis, right? Yes, this is from Fourier's law. This is from Fourier's law. Now we'll have to substitute this in terms of the respective axis. We'll have to substitute this in terms of the respective axis into the equation, right? We'll have to do this, substitute it with respect to the, with respect to the axis, that is x, y, z, into the equation. Now, how is it done? Now, from this particular equation, then I can say that Q subscript x dot is equal to negative k along x times a along x. If I say a subscript x, then we are trying to say that that particular area is perpendicular to the heat flux along the x-axis. Del t del x. Now for Q subscript y dot, it will be negative k subscript y ay del t del y. For KZ, it will be negative kz az del t del z. So we substitute this into the differentials here. Then we continue. But mind you, let me just tell you one thing now. There's one thing you need to know. There's one thing you need to know. We've already defined g as small g multiplying my dv. And I know since that is my control volume is a cube, then my volume, which is dv, is basically dx, dy, dz. Yes. Now, the time rate of change in the thermal energy within the control volume, what is it? Now, since we've selected an infinitesimal element, then my change can be, that is in terms of differential, right? So the time rate of change in the E, which is the thermal energy, time rate of change in the thermal energy within my infinitesimal control volume, then can be written as dE over dt if that control volume is truly an infinitesimal one. So I've written it like this. Now, you remember from thermodynamics. Now, the change in thermal energy of a material or a substance is what? It is the mass, in this case the m, multiplied by, that is the specific heat, right? And since we are talking about incompressible materials, then this is not actually applied to only incompressible materials, but then we are using incompressible materials to derive the equation. Then we say that Cv is the same as Cp. So I'm saying Cp multiplied by the time rate of change in, that is the temperature, del T. That is it. That is it. That is it. So this is supposed to be time rate of dm dot, because we are talking about time rate of change in the what? In the thermal energy within the control volume. This can also be written as this. That is dm times Cp del T del T. The small t is the time, the capital T is the temperature filled. Now mind you, the temperature here in this scenario, we've not done any assumption, so it depends on both spatial coordinates and then time. So my temperature here depends on both spatial coordinates and time. So note, I've not done any assumption here. Then we can substitute all these into the equation. But I also want to also do one thing. Now, my dm here, which is mass, can also be written as so. Now we said the density for that particular material is constant. Then we can say that density is equal to the mass dm over the what? Over the volume dv. Then we can say my dm is equal to, that is my density multiplied by my volume, dx dy dz. This is my mass. So what are we going to do? We are going to substitute everything into our what? Into the equation. Now, substituting everything into the equation, what do we end up with? Substituting everything into the equation, what do we end up with? We end up with that is negative del of x of negative kx, that is A. That is A along the heat flow. That particular area is perpendicular to the direction of the heat flow. And that particular area is actually, that is dy dz. So you can, let me draw a small diagram somewhere for you to get what I'm trying to say. Now this, if this is our infinitesimal control volume we selected, this is our x-axis. So if that is the heat flow is along the x-axis, then what will be the area? The area perpendicular to the heat flow is this particular area. And this particular area is what? That is, this particular dimension is along y, so dy. This dimension is along z, so dz. So that particular area will be dy times dz. So if the heat flow is along x, then the area is dy dz. If the heat flow is along y, then the area is along, that is dx dz. If the heat flow is along z, then the area is, that is dx dy. So you realize that that is the axis here, the derivative of the axis here does, the derivative of the axis here, right, is not the same as what is here. So whatever shows up here shouldn't show up here. That is basically the trick for knowing that. If you can't put this in your mind, let's draw your small infinitesimal diagram and understand what is going on over there. Yeah, let's proceed. So the equation will be, doing our substitution, the equation will be negative kx dy dz del t del x, right, minus, that is del y negative k subscript y, that is ay will be the x dz multiplying del t over del y, multiplying, no, this here is supposed to be dx, supposed to be dx here. If you check from, it's supposed to be dx here. Yeah, yeah, there's supposed to be dy here, plus, that is del of negative k z, that is dx dy del t del, that is z multiplying dz. Yeah, multiplying dz. So from here the job is done. From here the job is done. Let me write the right hand side of the equation. So the right hand side of the equation will be what? Let me not forget this, plus, that is the heat generated within the control volume. The heat generated within the control volume, which is J dot, will be what? That is my small j dot multiplied by the volume. And as I said, the volume is dx dy dz. Then this is equal to the time rate of change of, that is the thermal energy within the control volume. And we said that what? That will be the mass multiplied by the specific capacitor at constant pressure times, that is the partial derivative of the temperature field with respect to time. So that will be, and we know the mass. The mass is what? That's the density multiplied by the volume, dx dy dz. I strongly encourage that whenever you are watching these lecture videos, pick a paper and a pen, pick a writing material and write something, right? Write something and then follow the class. Yes, you will get a conceptual feel of whatever I'm doing. So this, which is the, this is actually the mass. So the mass multiplied by, that is the specific heat at constant pressure times del T del time. As simple as that. Now you realize that from this particular equation, that is the infinitesimal volume will cancel out. So dx dy dz cancels out dx dy dz. The same applies to here. You have dx dy dz cancels out. You also have dx dy dz, it cancels out. You also have similar thing dx, that's dx dy dz, they also cancel out. Then we can say that our equation is negative del x of negative kx, that is del t del x, right? Here is supposed to be negative, not positive. Yeah. Negative del y, negative ky, that is del t del y, that is, this is not supposed to be positive, is supposed to be negative. You can check from the previous steps. You realize it's not supposed to be positive, it's supposed to be negative, but this is supposed to be positive, so that is fine. Now we end up also getting del z of negative kz del t del z, right, plus g dot is equal to that is the density multiplied by my Cp, the density multiplied by Cp of del t del small t. So this is what we have left. So actually this is the equation. This is the general equation for conductive heat transfer. It is the general equation for conductive heat transfer. It can be written as that is negative times negative is positive. So I can say del of kx del t del x plus del y ky del t del y plus del z kz del t del z plus that is my heat generation per unit volume, which is equal to, that is my rho Cp del t del small t. So for this particular equation, it is general. We've not assumed anything, right? So here, this is what you need to know. Here, it is a what? An unsteady. It is unsteady. That is one. The material is not isotropic. Not isotropic. What do you mean by not isotropic? Meaning, for isotropic materials, my kx is equal to ky is equal to kz. Right? That is for isotropic. But then for not isotropic, that is, they are not the same. For not isotropic, they are not the same. They are not the same. And there's one thing you need to know. Now, generally, the K, which is the thermal conductivity, is a function of the temperature. Now, the temperature is also a function of some spatial coordinate, right? But then generally, that is if the material is isotropic, sometimes it may not vary with the spatial coordinate, but it may vary with temperature. But when it's purely isotropic, then if that is, it does not vary with spatial coordinates, then similarly, it also doesn't vary with temperature, because we know that the temperature depends on spatial coordinates, right, and time. And if that is my K also is a function of, that is, temperature, if my K is a function of temperature, then it translates that my K would also be a function of spatial coordinate. So if That is, if my material is not isotropic, then my K is different, right? At all along every axis. So along every axis, we have a different K or a different thermal conductivity for that particular material. So here realize we have an unsteady case. It is not isotropic, and here that is heat is generated within the control volume selected. Heat is generated. There's heat generation within the control volume selected. That is one thing I want you to understand, right? So this is the general equation. Note, let me circle it. This is the general equation. That is the general equation. There's a general equation. There's a general equation. This is a general equation. Now, let's make certain assumptions. Let us make certain assumptions. Now, let's say the material is isotropic. So for this case, let's say for case 1, isotropic material. What does it mean for isotropic material? For isotropic material, then Kx is the same as Ky is the same as Kz. So I can factorize my K out. So for isotropic material, Kx is equal to Ky is equal to Kz is equal to K. Then I can factorize K out. Then I can say that is del x, right? Del x K out of, that is dt del t del x plus K out del of del y of the expression, del y of the expression del t del y plus K del z del t del z, right? Plus my small g dot is equal to my rho Cp del t del small t. So here from here, you realize it is one quantity. It is actually, that is double, not double integration, but then double differential. So we can say K del squared T del S squared plus K del squared T del Y squared plus K del squared T, the temperature for del Z squared, plus my J dot is equal to rho Cp del T del small t. As simple as that. So you can see that clearly my K is constant. Then I can factorize that out. Then what do I end up with? Del squared T del xt plus del squared T del yt plus del squared T del z squared plus J dot is equal to rho Cp del T del small t. So from here, what can I say? You remember in vector calculus that if you have anything like this, right? If you have say that is the partial derivative of some particular quantity with respect to all the, that is coordinate. So del squared of this, del squared of this, del y squared plus del squared of this, del z squared. This is the same as saying that is the Laplacian of the quantity in the parentheses. So the Laplacian simply means that the grad squared. Laplacian simply means the grad squared. So the grad squared of the quantity in the parentheses. So for what we have here, we can say, let's move to the next page. For what we have, we can say that is K del squared del x squared plus del squared t del y squared plus del squared t del z squared plus j dot is equal to rho cp del t del small t. So this can be written as k, the Laplacian of the temperature field, plus j is equal to rho cp del t del small t. This one thing you need to know. Now, this particular equation is also for conductive heat transfer, but under certain assumptions. Under the assumption that the material is isotropic, under the assumption that the material is isotropic, under the assumption that the material is isotropic, under the assumption that the material is isotropic. Now, there's one particular quantity I haven't really introduced, which is thermal diffusivity. Thermal diffusivity is denoted alpha. It basically tells you how heat is diffused, right? How if you have a material and subjected to heat, that is how that particular material can diffuse heat, right? Can diffuse heat. That's basically what your thermal diffusivity. And thermal diffusivity is equal to, that is your thermal conductivity divided by, that's your heat capacity. This is basically your heat capacity, rho times Cp, your heat capacity. That is your thermal diffusivity. Then I can do one thing to the equation. I can say that is the Laplacian of the temperature field plus J dot is equal to, divided by K, J dot divided by K. I'm dividing through by K, is equal to rho Cp divided by K del T del small t. Then I can say that the Laplacian of my temperature field plus J dot divided by K is equal to 1 over alpha, and alpha is my thermal diffusivity, right? So yes, J dot is the rate. So yes, this is what we have. So you can also write the equation like that. That is, if the material is isotropic, that is what we use. But then for this equation, one, the temperature depends on both spatial coordinates and then time as well. There is heat generation within your material. That is one thing you need to know. The only assumption over here is that, now if you include the general assumptions we made, the assumptions will be made. If you include the general assumption, we said that one, that is, there shouldn't be any bulk motion of the molecules of the individual particle within the solid material. That was an assumption we made. We also said that is all the quantities are constant, right? That is except thermal conductivity, right? Initially, that's what you said, except thermal conductivity. Cp is constant, density is constant, Cv is also what? Constant. That's what we said. But then at this point, we are assuming that the material is isotropic. Then we can say that is here, K is constant, density is also constant. That is, Cp is also what? Constant. That's the assumption you can make. And also there's no what? There shouldn't be what? Any bulk motion of what? Any bulk macroscopic motion. Any bulk macroscopic motion of, that is, the individual molecules or particles within the material. Within the material. That is it. Within the material. Now, I also want us to say something. Let's just say for the second case, that is we have one isotropic material and two, no heat generated. No heat generated within our material. then what would the equation be? Now the equation will be initially was the Laplacian of the temperature field plus G over K is equal to, that is 1 over del T del small t. This is G dot. Now, if the material is isotropic and there's no heat generation, then G dot goes to 0. Then we have the Laplacian of the temperature field is equal to 1 over alpha del T del small t. Del T del small t. Now, case 3. There are so many cases. It all depends on the assumption you get or you make. It all depends on the assumption you make. Now, the third case is when one, the material is isotropic, and then 2, we have a steady flow heat transfer. What will our equation be? Now our equation will be steady flow heat transfer. Then it means del small t goes to 0, because when you have a steady flow, then properties for a control volume, then all the time, the time rate of change of all the properties will go to 0. But for control mass, the time rate of change of all the properties will go to 0, except for the mass, because we cannot say time rate of change of mass, because that is a control mass. But then for a control volume, the time rate of change of all the properties will go to 0. So the time rate of change of the temperature field will go to 0. So what do we have? So our equation becomes, that's our Laplacian of the temperature field plus, that is G dot over K is equal to 0. That's how it's supposed to be. Plus G dot over K is equal to 0. Now for the fourth case, you can assume more other cases. You can also assume more other cases yourself. But then for the fourth case, I'm going to talk about. Now let's just say you have the material is isotropic. That is, you have a steady flow heat transfer. Then the third one is no heat generation. Within your control volume. Then what would the equation be? Then your equation becomes the Laplacian of your temperature field is equal to 0. That is it. Now, before we go, I want us to talk about one particular concept, one simple concept. We call it, that is the thermal resistance. Now, whenever you have two systems, and those systems are described by, let's say, similar equations or say similar boundaries, then we can say those two systems are analogous. So a typical example is electricity or electric current flow, right? Now, what causes current to flow through a resistive element? It is the potential difference. So the potential difference causes, that is, current to flow through a resistive element, right? So there is current flow. This is our resistive element, right? This is our what? Potential difference of V1, V2. This is our potential difference. So what will be our current? Then our current will be, that is the potential difference, V1 minus V2 divided by the resistance. We can actually link this to heat transfer. In this case, conductive heat transfer. How? Because, that is, we can also say we have a solid material, or we have a material. Now, through that particular material, heat flows. So the heat flow rate is Q dot flowing through that particular material. Now, what causes heat to flow? That's basically what? Your temperature gradient. So T1, T2, or if I should say the temperature difference, T1, T2. Now, the resistance, right? What resists, that is the heat flow through that particular material, is what we call the thermal resistance. R subscript TH in this case for conduction. Now, what will be the thermal resistance for? What will be the thermal resistance for a material when we have a conductive heat transfer? What will it be? What will it be? Now you remember from what I told you. You remember from Fourier's law that when you have, say, Q dot is equal to negative K A, that is del T over, say, del X. Let's just say the heat flow is along X, del X. Now the temperature difference is the what? Is the del T. The temperature difference, the del T. Then I can say that comparing these equations, so equation 1, Q X dot will be equal to, that's the temperature difference, which is what is driving our what? For this one, the difference in potential is what is driving the current. For here, the difference in temperature is what is driving the current. So I can say del T negative divided by what? Divided by, that is, so whatever is here will be our what? Our thermal resistance. The same thing here, whatever is here is your electrical resistance. So whatever expression we get here will be our thermal resistance. Then our thermal resistance will be del X divided by, that is, Ka. So this is our thermal resistance. This is basically our thermal resistance. Yeah, so I'll end the class here. In the next lecture, we'll talk about heat conduction through plane walls. Heat conduction through plane walls, and see if we can solve some problems. Have a wonderful day.